All right, everyone, thanks for coming. Welcome to the first meetup, or I guess session, of the Computational Biology Reading Group. This is the group that Paul Castellano, Matthew Hershey, and I have started. So I think some of you know me and Matt. Paul's a new hire at DMPI, working in the Hershey lab, and he's an actual computational biologist. So if I say anything wrong, he'll be there to correct me and help everyone else. So also welcome to whoever is watching this on YouTube. I brought some stickers, some Tidyverse stickers, so this is extra motivation to actually come in person. All right, so just broadly, I'll just cover some of the goals of this reading group, and then we'll proceed to actually do some coding. So the primary goal of this reading group is to learn how to use R specifically to answer questions of biological interest. Depending on how this meetup goes, this could eventually become a reading group where we discuss how to use Python, Bash, Git, and other relevant tools, but we'll begin with R. I know this term gets thrown around a lot, building a community. It's almost lost its original meaning, but genuinely, it would be so great to have the disparate expertise and voices that are at the DMPI and online, I guess now, like, come together and help each other address problems of interest. And eventually, as time goes on, I hope that we can build a repository of the code that we go through, the data sets that we look at, and these recordings that we make. So I assume everyone has R and RStudio installed. If you don't, these are the two links that you can click on to go ahead and do that. It's probably best to have the most recent versions of R and RStudio, but if you don't, that's okay. If something breaks later on, you can always upgrade. And the good thing about R and RStudio is they're pretty much trouble-free. You install it onto your machine and you're good to go. All right. So a few weeks ago, I came across this book called Computational Genomics with R, and I just thought this looked like a really nice, comprehensive book to increase my understanding of this field that I'm interested in and also fill in gaps. And as you can see, this book begins with a lot of chapters that are maybe not that relevant to us because it's just like, what is genomics and things like that. Although if you need a refresher, these are some nice chapters. And then it goes straight into an intro to R, but then it goes all the way to multi-omics analysis. And we hope that over the course of this meeting group to eventually start doing analyses like that. However, Paul let me know about this book called Omics Data Analysis, which also looks really great. So although the initial plan was to kind of follow one book, I think it makes sense to at least use these two books to start off with as source material because they're complementary. So we'll be using material from both books, but hopefully in a way that isn't too confusing. And I know I'm preaching to the choir, so I won't spend much time talking about why computational biology is important, but I did come across this really nice paper called All Biology is Computational Biology. And it's a really great short article about computational biology, but I really like this one part where he says, we don't refer to wet lab biologists as pipette biologists. We don't refer to people by the tool they use. So instead of calling people computation and computers and programming, these are all just tools. So why silo biologists into these different groups based on the tools they use? And I thought that was a nice way of reframing this so that it makes all of this just less intimidating, especially to someone like me. Okay, so for today, we're going to do three things. We're going to create an R project in RStudio. We're going to install, so we made a package, for want of a better name, we're calling it CBRG. And we'll go through why we made this package and what the potential benefits of using a package might be. And finally, we'll actually do some exercises. So before we begin that, So this is the so this package lives on GitHub, and this is what it looks like. And the README page has just some relevant information about installation and what this package does and how to use it. And it also has links to the books that I mentioned. And this is something that we'll be developing as the class goes on. Oh, also there's an obligatory hex sticker that is required for every package. And this has a little heat map, sorry, not a heat map, a volcano plot using the Golub dataset, which is this iconic microarray dataset from, I think, 1999. And that dataset did a lot to spur advances in big data and computational biology. So it's historically very important. A couple of other things about this GitHub page. It has a discussions page. So you're welcome to introduce yourself. And just as importantly, if you have any questions about anything, there's a Q&A section. And why do this as opposed to Slack or just sending emails to us? It's nice that there's this, again, repository of questions, because a question you have is probably going to be relevant to someone else. And then there's a welcome section if you want to introduce yourself. Sophie from Amsterdam has introduced herself already, so that's great. Welcome, Sophie. And then finally, if you have any issues with this package, obviously email us. But again, in the spirit of helping anyone who might need help, you can also post what's known as an issue. And you just literally click new issue and say, function X is not working, please fix it, something like that. Okay, so I'm going to go ahead and assume that people have RStudio. And if you do, please go ahead and open RStudio. So I already have it open. I'll give this like a second. Also, yeah, it goes without saying, but if you have any questions, please ask, interrupt. Okay, so assuming that you have RStudio open, I mentioned creating a project. Now, we could do all of this without creating a project, but the advantage of it's a good habit to get into every new thing you make. So it could be an experiment or a real life project or something that you're working on, or like, for example, this, a meetup. They should all have unique projects associated with them. And this is a nice way of organizing your code. So to create a new project, it's really easy. You just go to File and just click on New Project. And it'll ask you to save, don't save. And you should pick a relevant directory. So click on New Directory and then click on New Project. And I'm going to pick a relevant directory. And I'm just going to call it CBRG. Meetups. So you can call it whatever you like. And RStudio takes a couple of seconds to make it. And as you can see, this is an empty project with nothing except this project file and this this .rproj file. And that's just a way of keeping track of the various projects you have on your machine. And so now, whatever you save in this environment, or if you do decide to save anything, it'll all be within the self-contained environment. And once you're done with it, you can close your project and then move on to other things. And then if you want to come back to this, or next time we have a meetup, we just reopen this project. Okay, so now that you have this project open, in your console itself, so we can go back to, we can go back to the GitHub page. And if you go to the README, it'll have instructions of how to install this package on your machine. So that's this here, this installation part here. Now, to install this package, you need to have another package installed called DevTools. And as time goes on, we'll describe packages a little more. I mean, there's not much to it. A package is just a convenient collection of useful functions, code, data associated with a certain task or tasks. So if you have DevTools installed already, that's great. you can then just go ahead and run this devtools : install _ GitHub, and then the name of this repository in inverted commas, and then specify that force equals true. One thing about this package is we will be regularly updating it. So it will be, unfortunately, when it gets updated on GitHub, it won't automatically get updated on your machine. So to keep up to date, you will have to run this command every so often. Once a week, maybe before each meetup would be a good time to do it. So if I go here and just enter this into my console and run, hopefully you should encounter no errors. And it's a pretty, right now it's a really lightweight package, so it. Okay, assuming it's installed, and please interrupt me if there's any issue. Cool. So this package has, so we mentioned that we're using these 2 books as source material. This package is a way of keeping things organized. And so once you have this package installed, you won't have to copy paste anything from elsewhere or download anything from elsewhere. Everything will be available through this package. So this package has a few functions associated with it. So I just went through this mini presentation. These slides will also be in the package. If you wanted to see this presentation on your computer, you could do, well, you could run first library to load the package that you've just installed. So it'd be library CBRG. And then to see a particular presentation, maybe after class or, after the session, you could just do launch slides and then specify. I've called it a class. This is not a course. These aren't classes, but maybe I could have called it session. You do class equals 1, and I'm not going to, well, might as well. And if you run that, you'll see that it opens up the presentation in a new browser. For today, to go through the material, we'll use another function called launch _ class. That's all the material we need for today. And again, we need to specify what class it is, and it's class 1. If we run that, hopefully, you should see a new document open up in your project. And again, this is just one type of document you could use to enter and execute code. It's an R Markdown document that has, that's a very versatile document format. You could also just simply use an R script, which a lot of people do, but it's more limited. So we're going to use this R Markdown format, and it's becoming more and more popular. Okay, so if everyone has their 01 _ class.rmd, we can actually now just go through the code. I should say that I hope that today's session is useful, but I also hope that it's the least interesting session we have, because it's just level setting and just getting used to the language. So if you are familiar with R, this will be redundant, but hopefully it'll be of use to people who aren't. And so in today's session, we'll just go through some basic R commands, and next week's session, we'll go through some basic plotting. But the real computational biology relevant material will start the following week. Okay, so this is an R Markdown file. It has different what are known as code chunks, and these are chunks that you use. These are things that you use to enter and execute code. They're special because if you entered code in a non-chunk area, nothing would happen. You'd get an error. And the great thing about R Markdown is you can run R code, but you could also run code from other languages like Python and Bash. And I did mention that these are other languages that we might cover in the future. So you can actually just do all of that through RStudio. So all our Markdown documents begin with this special chunk called a setup chunk. And as the name suggests, you use it to set things up. And each of these chunks I've put in what are known as comments. So these are all, this is all refers to text that has a pound symbol at the start. And those are just either they describe what the code is, or as the meetups proceed, when we start doing more and more kind of real exercises in a session, they will be like questions, do this or do that. So as with any other Markdown document, you go in sequence. So to run the contents of a given chunk, you can click this little play button here. And so that just loads this relevant package called tidyverse, which again, I'm wrongly assuming everyone has. If you don't have this package or any other package, one way is to see where this package exists. So if it exists on GitHub, you would use the install_GitHub command you just used. If it lives on this thing called cran, as tidyverse does, one really simple way to install it, actually, no, I've put in the code to install the tidyverse package, but I've just commented it out. So that's what you would do. You would do install .packages and the name of the package. All right, we begin with some basic R. As I say here, R is can just be a glorified calculator. So you can do some simple arithmetic operations like 2 + 3 × 5, noting the order precedence, so multiplication before addition in this case. Now, you could run all these, so you can see there's multiple lines of code in this one chunk. You could run all of it and see the output of all of it just by clicking play. But if you wanted to see the output of just one line at a time, you can, one handy way is to just do, if you have a Mac, command, go to that line, the end of that line. So in this case, line 24. And then you could click Command Enter or Control Enter, depending on what machine you have. And I realize that things might be a little bit difficult to see, so I'm just going to increase the size. So you can see that 2 + 3 × 5 is 17, and not 25. All right, and then R has a lot of useful functions because it started off as a statistical programming language, so it has a lot of relevant functions built in. So if you wanted to create the work out the natural log of 10, you would do log 10. And if you wanted to do base 10 log, it would be log 10, 10. And you can work out the square root of a number, something called abs. And that just means it takes whatever number it has and gives you the positive output. So if it's a negative number, it just changes the sign to positive. Let's say you didn't know that, and it wasn't evident of what this function does. To look up the what the function of a function is, you can use this question mark, and then you write the name of the function without the parentheses. So let's say I have no idea what this abs function is. I just do question mark abs, and you get all this relevant information on the bottom right-hand corner here. And so it says that it's from this package called mathfun. It describes it, gives you the usage. Now, in this case, it's a very simple function, so the documentation isn't particularly useful. But as the functions get more and more complicated, this is a go-to place to find out what the function does. And for me, the most useful part is almost always the example section, which is unfortunately right at the very end. Okay, so we'll move on to the different data structures there are in R. So if you have attended any of Matt's Teddy Biology, either the bootcamp or the meetups, you will have seen that most of the data structure that is primarily used in those sessions, was used in those sessions, is what's known as a DataFrame, also sometimes known as a Tibble, which is a slightly different version of a DataFrame, and we'll get to DataFrames. There are other data structures that are really important, especially in computational biology. So we'll be covering some of those now. So a really simple data structure is this thing known as a vector. Also, I think it's formally referred to as an atomic vector. because each vector is just a collection of objects, data types that are a collection of objects that are all of the same data type. So you could have, in this case, on line 43, we're constructing a vector called vec that just has numbers. So you couldn't, for example, in this vector, put in a string. That would throw an error. You could have another vector that is only consists of strings, but you cannot mix and match. That's why they're atomic. To build a vector, it's super easy. You just use this C function, and C stands for both combine and concatenate, I believe, but it's just C. And you just put in whatever you need to put into this vector, separated by commas. And again, assuming this is the first time you're using R, to save the output of anything, you need to assign it to an object. And in this case, we're assigning this vector that we're creating, we're assigning it to an object called vec. Now, you could just as easily do vec equals, like you would in Python or another language, and that's acceptable. But it's preferred syntactically in R to use this assign operator. And again, it's also preferred to do a left assign. You could also do a right assign, that's allowed, but this is preferred. And so if I just run this, I now see that in my global environment on the top right-hand corner, so the top right-hand corner, we can see our environment. So the global environment just shows you all the objects that exist in your session. And right now, this is the first time we've actually created a new object. And we can see it's up there. It has the name vec, and then you can see the first few entries of vec. Yes?
We have a question from the audience. What are the differences between arrays and vectors in R?
What are the differences between arrays and vectors in R? So as I understand them, vectors are one-dimensional. So like they look like here. So one-dimensional meaning you just think of like a number line. Arrays are a broad term that refer to vectors, matrices, three-dimensional arrays, and multi-dimensional arrays. I actually have never used, even though, I use vectors and matrices, which are technically arrays, but I've never actually used arrays in higher dimensions in R. I hope that answers that question. So the good thing about vectors, and as the name suggests, is they allow for what's known as a vectorized operations. And this is especially important when you're dealing with big data like computational biology data that can get huge. So to show you what I mean by that, if you look at line 46, we're again applying this abs function to this new vector that we made. And if we look at the output, it's a simple function. All it did was convert all the negative numbers into positive numbers. The important thing is it did this in what's known as a vectorized way, meaning it did this in a very efficient parallel way. So it worked out, it applied this function to all of the inputs of vec parallelly. If you are familiar with for loops, where you go through each element and you do something to that element, you could just as easily write a for loop to convert all these numbers into positive numbers. And that's fine if you just have 5 numbers, things happen in microseconds. But if you had 1,000,000 numbers and you ran a for loop, it would take a long time to run through that. So R kind of has a lot of these operations that are vectorized that introduce efficiency. So similarly, if you wanted to work out the square of each element, you would just do vec, and the raised to symbol is this, I guess you call it a raised to symbol, and then 2. And if you wanted the cube, you would do 3, and so on. There are many useful functions that you can apply to a vector. So for example, so it's obvious here that there are 5 elements in this vector, but as I said, if there were 5,000,000, and you wanted to see how many elements there were in the vector, you could use this length function. And finally, sometimes a vector has elements, only has a subset of elements that you're interested in. And so and there are various elaborate ways of subsetting a vector that I'm sure we'll cover in subsequent meetups, but this is a really simple example of doing it. So typically when you subset really anything in R, but a vector in this case, you use square brackets. So you do vec, the name of your vector, vec, and open close square brackets. And in this case, when I do 1:3, that means I want the first 3 elements of vec. So I do vec, and then it goes 1, -2, 10. All right. So speaking of arrays, we now go from a one-dimensional array, which is a vector, to a two-dimensional array, which is a matrix. Again, just like with the previous tidy biology classes and meetups, we didn't explicitly discuss this data structure. And one reason for that is the tidyverse functions don't accept matrices. They only work with data frames. However, matrices have, again, some nice features that data frames don't, because like a vector, a matrix can only contain objects of the same data type. So things work faster with a matrix than with an equivalent data frame. And also there are a lot of functions that are in these computational biology packages that only accept matrices and no other data type. So one way to make this kind of like joke matrix is to just do is to use this just as you used well, actually, to make the vector, there's no vector function that I'm aware of. To make a matrix, you actually have a function called matrix. And one way to make a matrix is to just give it a vector. So in this case, I've given it C with 9 elements. And then you specify the number of rows. And if you specify the number of rows, it'll automatically work out the number of relevant columns. So in this case, if there are 9 elements in 3 rows, there will be 3 columns. So you create a square 3 by 3 matrix. Oops. And the output, it looks like this. And if you look at the kind of row labels and column labels, that's R's way of telling you how to extract individual elements from your matrix. So it's sort of giving you a little cheat code there. So I'm going to do the same thing here, but then just assign the output of this matrix to this object called M, and we can now take a look at this new object. So just as we had length for vectors to see how many elements there are, with matrices, it's always useful to know how many dimensions your matrix has. So in this case, or rather, how long each of the 2 dimensions is. So in this case, it's a square matrix, it's 3 rows and 3 columns. So if you just use the simple dim function, you get the dimensions 3 by 3. Subsetting a matrix is a little bit more complex than subsetting a vector because of this additional, because it's 2-dimensional as opposed to 1. So in this case, if you were to do, you need to keep track of both the rows and the columns. So again, subsetting works in the same way. We use square brackets, M, in this case, M followed by square brackets. And typically, there are 2, I guess, spots or places within these square brackets. One is on the left-hand side of a comma, and the other is on the right-hand side. Whatever goes on the left-hand side refers to the rows of your matrix, and whatever goes on the right-hand side refers to the columns. So if you look at line 72, what that means is I am asking R to give me the first row, because it's 1 before comma. And if there's nothing after the comma, R reads that as I want everything. So what that means is if I run this line, I will get just the first row, but all the columns. So that's 152, which, if you remember what M looks like, is just the first row. Similarly, if I want just the first column, I would do kind of the opposite. I would do M, open close square brackets, a space. I haven't actually put a space here, but we can, just for clarity, comma, and then which column do you want? In this case, I want the first column, so I just do that. And 1, 3, 2 are the elements of the first column. If you want to do something a little bit more involved, you want the first 2 rows and all the columns, you would do something like what you see on line 78, M, and then 1 to 2. So that's row 1, row 2, comma, space. So I want all the columns. And you can mix and match like this to extract relevant parts of the matrix for your analyses. Does anyone have any questions about vectors and matrices? And for the linear algebra fans, there are ways of doing matrix multiplication, working out the determinant, things like that. That's all built into R. Okay, so now we're moving on to a data structure that should be familiar to everyone, the data frame. And again, we can think of a data frame as like an Excel spreadsheet because it's tabular. I guess it's not strictly, because in Excel you can have columns of different lengths. One constraint with a data frame is that all the columns in a data frame have to have the same number of rows. So again, if you've attended any of the tidy biology classes or meetups, you will have seen that we start off with a data frame, and then we do things to that data frame. In R, you can also construct, and when I say do things to those data frames, usually it's typically something that we import from Excel or wherever. You can just construct a data frame from scratch within R, and there are many ways of doing it. One way, building up from this vector approach, is to construct a few different vectors. So in this case, if you look at lines 85 to 88, this code will, if you run through it, will make 4 different vectors. And you can see that these vectors are of different types. The first 2 vectors, CHR and strand, they have character data types. Whereas if you look at stat and end, they have numeric data types. But notice there's no mixing and matching. So if I just run through them line by line, you can see that our global environment is now populated with 4 new vectors. And what you can do with these vectors is, because they're all of the same length, each vector contains just 4 elements. You can take all of these vectors and use this new function called data.frame to make a data frame. And like I said, there are many ways of making data frames. This is the kind of base R way. And if we run this, we get this new object called myData. So as a slight aside, if you're wondering why we're introducing these base R functions when there are equivalent tidyverse functions, one reason is, like I said before, you can't apply those tidyverse functions to, for example, matrices. So it becomes essential to use these base R tools. The second thing is, a lot of people still just prefer using base R. I shouldn't say just, prefer using base R. And so when you're reading other people's code, if it's not in the tidyverse, if they haven't used dplyr or ggplot, it's still useful to be able to understand their code. So it's not that much more effort learning some of these simple base R ways of doing things. So we created a new data frame called myData. If you want to quickly look at this new object that you've created, you can just click on it in your global environment, and you see we've combined our 4 vectors to get this nice tabular data frame of fake chromosome data. All right, and so the good thing about learning how to subset a matrix is we use the same approach to subset a data frame. And actually, this is where the tidyverse really shines, because subsetting data frames in the base R way is a little tricky and not particularly intuitive, but the tidyverse way is. So in this case, let's say I want all the rows from my data frame, but I only want the first column and the third column. I could do something like this. Do my data, and again, open, close, square brackets, a space, meaning I want all the rows, comma. And if I want 1 and 3, for example, if I took away this C function and I just did 1 and 3, kind of naively like this, and I ran it, I would get an error message. No, I wouldn't. Okay, I would get an output that is not what I want. So to tell R that, no, this is in fact the first and third column, you'd have to use this C function. And you can see the output here. It's the same data frame, but we only have the first and third column. So that's the base-hour way. The deployer way of doing the same thing is if we want to if we're okay with having all the rows, but we just want, but if we just want certain columns, we would use what's known as the select function from the deployer package. And this is, again, as the meetups progress, we'll introduce more and more functions, both from base-hour and the tidyverse. But if you want to get a head start on that, again, all the tidy biology classes and meetups are on YouTube, so you can use that as a refresher if you need to. All right, so we have select, and then we have to give select an input that we use to select things from. So we use a DataFrame myData. And then similarly, just like in the base-hour way of presenting this columns 1 and 3 in this combined function, we do the same thing here. And if we run this, we can confirm, we scroll down, we get the same output. Now, moving from this way, so another great thing about the tidyverse way or the deployer way is it prevents, so we just did this one select. Let's say we wanted to do more additional things that are more complicated. We could create intermediate data frames, which can get a little bit tricky because your environment gets populated with all of this clutter. Or you could kind of put everything in one line that looks super confusing and is error prone. So to avoid either of these two things, some people made what's known as the pipe, which is this object here on line 99, this percentage greater than percentage sign. And all that means is it's taking whatever is to the left of it and using that as the output of that as input for the next line. So in the case of the first input, my data, we're not doing anything to it. So we're just taking it. And then, so that's a good way of thinking. Whenever you see this pipe, you always think, and then we use it as input for the select function. So the difference between line 96 and lines 99 and 100 is you see that this myData object is no longer within the select function. That's what the pipe operator is doing. You can think of it as an assembly line in a factory. Person A does something, passes it on to person B, who does something, passes it on to person C. And so this way, in this specific case, it's overkill. It doesn't really make things better, but it's a simple way to see what's going on. And you can confirm that the output is the same. And similarly, if you wanted to do, so in this case, I selected specific columns. If you want to choose specific rows, and notice I say choose because it's confusing to say select rows using filter. Anyway, so I choose rows. You need to choose rows, or you can choose rows based on some criterion. So in this case, this myData pipe operator and then filter means that I only want to choose chromosomes that are chromosome 1. So I use this, importantly, I use this equals to operator. Because in R, if you just use equals to, that is telling R that I want to assign what's on the right to the left. I don't want to do that. I want to do a comparison, a logical comparison. So if you want to do a logical comparison, you do 2 equal to signs instead of 1. And if we run that, we get this. If you wanted to do the kind of equivalent to select for like the filter equivalent on rows, so you wanted to choose certain rows based on their index, you would use what's known as the slice function from the tidyverse. But that's just an aside. Okay, so yes.
So when you run those commands in the console, it shows essentially the command
Yes.
you enter. It doesn't show the result of it visually.
Mm-hmm.
What is the difference between like when it's doing that, it's making the computation, but it's not showing it to you.
Right.
Versus sometimes, versus what would you do differently to have to be able to see?
Good question. So the question is, specifically in our Markdown, when you do this like Control Enter or Command Enter, you see that something is happening. And in the console, you only see a copy of the code you ran, but you don't see the output. To see the output, you have to scroll down to the end of your code chunk, and you see the output there. This is just a formatting thing with our Markdown. In fact, a lot of people, you can change this in the settings. I don't quite know off the top of my head how to do that now, but you can change it. And so then you see the output there. Conversely, not conversely, but I guess additionally, if you wanted to see both the code and the output, you can just copy paste that into your console. And there you see the code and the output. But that's a good point. Sometimes, especially when you have super long chunks, it looks like nothing happened. Okay, so that was using the pipe operator and just kind of showing you very quickly how Besar and tidyverse are different and what the relative strengths are, although the tidyverse is probably stronger. Now, with this pipe operator, where it really shines is when you are chaining multiple commands together. So for example, lines 107 to 109, if you wanted to do both of the above, you want to just choose rows that have to do with chromosome 1, you only want to select the first and third column, you can just chain it easily like this with this pipe operator. And again, you scroll all the way down and you get the output. And similarly, for lines 112 to 114, it's just the same output. But if you wanted to save it as an object, you could just use this left assign and save it as an object called mydata_2. So I promise that this will be hopefully the only meetup where there's a lot of, where it's mostly just talking. There'll be more doing as we proceed. But having said that, this is the first time I'm going to ask you to do something. So just as an exercise, could you reproduce, you don't have to save this as a new object, so could you reproduce lines 107 to 109 without using a pipe? I'll give everyone like a couple of minutes. And also, any questions can be asked. Any help is needed. All right, so, and the reason I'm asking you to do this exercise is not so that you can know how to do it without the pipe, because as I said, doing a lot of these things without the pipe is kind of silly. It's really just to see if you can do it. So I'm going to actually just go ahead and start. Is everyone done? Did you confirm that you got the same output with and without the pipe? I'm going to go ahead, and so I'll see if I can do it without introducing any errors. So the logic of converting from the pipe sequence of doing things versus doing things in a non-pipe way is, instead of going adopting the sequential approach of top to bottom, you go inside to outside, which itself is more confusing, I find, than top to bottom. So what I mean by that is the alternative to top to bottom with the pipe approach is this inside out approach. So you would first start with the filter function. You put in my data, and then what are you filtering? You're doing this chromosome equals chromosome 1. And then, so this will give you some kind of output. That becomes the input for your select function. So you nest your filter function within your select function. And straight away, when I start writing it like this, I see this X because R is reminding me to put end parentheses. Already things are getting, for me at least, a little confusing. And it's after that, second to last parentheses. I put in a comma, and then what am I selecting? I'm selecting columns 1 and 3. If I run this, you get the same output as before, but I struggled even to write this simple command. So that if I were to add a third chain or a third element to the chain, this would get very confusing. Okay, and then just as a reminder, dplyr only works with data frames and not matrices. So yeah, that was just a super quick-fire overview of some of the basic data structures and data types in R and some really simple functions. But as I said, as opposed to divorcing the learning the language from the actual computational biology, we will pick up relevant programming skills as we go on when we do our actual kind of real life analyses. But I thought it would be useful to just have the first meetup just be about these simple functions. And the final thing I want to talk about is the very important data importing steps. There are various ways to import data, both from your machine and from elsewhere. And there are lots of functions that have been built to deal with various data types. Fortunately for these meetups, we'll predominantly be working with, no, there'll be some exotic computational biology data types also, but a lot of them will be CSV files, tabular files. Again, confusingly, just as there is as you saw multiple equivalents, base R equivalents to tidyverse functions, there are base R equivalents to these tidyverse import functions. I would suggest sticking to the tidyverse functions because they're just a little bit more predictable and user-friendly, even though a lot of the code you will come across, especially in computational biology vignettes or books, will be using the base R way. And the difference is really subtle. For the base R approach, for example, if you had a CSV file, you would use read.csv. And this can get confusing, I found, when you're reading a tutorial or a vignette and you write read_CSV, which seems like it's just a slight change. You can encounter lots of errors. So this is a very common mistake people make, this dot versus underscore. So I would say do your best to stick to underscore, but read.csv is also fine. So read_CSV, as you can see from here, comes from the reader or the readr package. And in this case, it's super simple. This CSV file that I'm importing actually exists somewhere on the internet. So you can put in URLs that end in .csv as input. So this is what I said about, you could either get the CSV from your machine or you could get it from elsewhere. So in this case, I'm getting it from elsewhere. And then it's especially important when you're importing something to assign it to something. Otherwise, you just imported it and nothing's really happened. So you can I've assigned it to this object called Golub subject. So actually, this is the same data set I was talking about, the 1999 pivotal microarray. It was by this group called Golub et al. So if you are curious about this data set, this is what it looks like. It's a microarray data set, and it has plenty of columns that refer to different patients. And that's really it. In the last few minutes, I did want to bring up, so what we're going to try to do is, as I said, hopefully, certainly from not next meetup onwards, but the following one, there'll be a lot more exercise content. And we'll be using these Markdown files that can be launched from the package. After the meetup, if you want to sharpen your skills or do some kind of practice, we're also making quote-unquote homework Markdown files. None of it is compulsory. And to run that, again, you can go to your console. And since you've loaded the CBRG package, just as you launched the file, for the in-class exercise for today, there's also an equivalent homework function. So launch_homework, and we specify what homework we want. Right now, there's just one. And it opens up this document here. And the kind of homework for this week is very gentle. There are only 5 questions with hopefully straightforward questions. And yeah, some of it is code that is improperly entered, and others are just empty code chunks that you are encouraged to fill. And in the event that there are any concerns or you want to compare this to quote unquote the right answer, you can use the same launch underscore homework function. It has an argument called show underscore answers. You can set that to true if you want. Remembering to write, capital TRUE. And it'll open the same document, but with all the answers. So if you have to cheat, that's what you would do. All right, 7 minutes left. That's kind of all we have for today. Are there any questions, or either about what you saw today or what will happen? Oh, also, before you answer that, I will send out a questionnaire. I promise just asking a few questions, mostly to do with trying to get a sense of what the level or self-perceived level of computational biology experience people have. And the second is just curious to see what people's specific interests are. So for example, if we get a lot of votes for proteomics, which I imagine we will, but not as many for transcriptomics, we might privilege proteomics, the proteomics chapter over the transcriptomics chapter. Maybe. But I will send that out sometime tomorrow. All right. Thank you once again. I really appreciate the interest, and I hope to see all of you next week.